mathematical, just previous slide, I just want to read the title. Title, first page. Yeah, I'm just talking on mathematical modeling, and in particular, drag flow through porous medium. Because mathematical modeling is a very hot topic. Ultimately, if you are able to model using mathematical concepts, then you can flourish. So, the next. So what is mathematical modeling? What is mathematical modeling? Simply speaking, is a description of a system using mathematical concepts and languages. There are a lot of things happening in and around us. The first and foremost thing is you should understand it. You should understand, then you can solve the problem, any problem. Let it be a personal problem or a scientific problem. The first and foremost thing is you should understand it. Then you have to use the concept of mathematics to frame it. That's the next stage. So the process of developing a mathematical model is termed as mathematical modeling. There are a lot of applications you have seen. You may ask why modeling is so important. See, for example, in mechanical system, if you want to do some experiment and get the data and output kind of thing, it takes a lot of time, a lot of resources, etc. But if you model the same problem, then maybe initially you have to spend a lot, but when you change the parameter, you don't want to repeat the experiment. So from the model itself, you can get the output, that kind of thing. So it will conserve, your resources, and you will get best result like that. You might have heard about a new model, about cars, 2002 model, 2003 model, kind of thing like that. Previously, ambassador car, So they say Mark 1, Mark 2, Mark 3, Mark 4, like that. So from Mark 1 to Mark 4, it is years together. Now every 6 months one car is coming. How they are developing a car? First, you have to see the fluid dynamics. When it moves fast, then how the fluid flow, how the weight balance and all these things you have to see. What is the stability kind of thing. Previously, they are doing all these experiments in laboratory when your computational system was not strong. Now they create mathematical model, they simulate, they understand what happened. What happened when it collide? What happened when it moves more than 100 kilometers? Or when reduce the speed? All the shape is not just for the beauty. So beauty plus science. So using mathematical concepts, they bring with a model. That's why we say 2000 model, because every 1 year, model was coming. Not every 1 year. We said 2002 model means it is built that time with minor modification, there come new models and all. Okay. So the process of mathematical modeling is, first step is you have to understand the system. That's why I meant by start. First you have to start learning things. Then you have to understand what are the parameters based upon that. Then you have to make a lot of assumptions, because solving problem is not that easy always. So we make a lot of assumptions. Let it be like this one. Let the initial value be 0. There is no opposing force. These kind of assumptions I can make. See, I'm going to drag this one. I'm just carrying this to this position, applying some force. What is happening? The friction, bottom friction, that matters. Then because of this flat plate, there is some air resistance. So I have to add all these terms in the model. If I'm not adding, I have to make, if I don't want to add, then I'll assume that this opposing force is not there. But the problem is the system have that much error. If you want more accuracy, you want more assumptions. You have less assumptions. If you want more accuracy, your number of parameters and all the terms and all these things much more. And it is quite difficult to solve. That's a problem. So if you want to have a feasible solution, then you have to make assumptions. Assumption is ideal cases. But actual case is quite different. All the models, E is equal to HI, Schrodinger equation, they made a lot of assumptions over there. Because that time they cannot solve the equations. You know that now E is equal to HI, that is eigenvalue system, eigen system. So they reach to that extent by making a lot of assumptions. So first you have to understand the problem. What is your requirement? What is the accuracy you need? Based upon that, you have to create the assumption. It is totally up to you. The second stage is formulation of the problem, formulating the equations and all. That is purely mathematical, because for example, there are a lot of rules. You are not creating any rule. F is equal to ma, not created by you. But most of the models you use F is equal to ma or Kirchhoff law. or all these things. It is already defined. You should understand which rule is applicable for you, and you have to formulate accordingly. Then third thing is solution. One more thing is boundary condition. The problem what I am doing, initial or boundary condition will be different. For someone else requirement, initial and boundary conditions are required. So based upon the problem, you have to decide the conditions. Based upon condition, the solutions are there. No two equations are the same, I can say. You talk about wave equation. You know about wave equation. What is wave equation? Dou square u by dou x square plus dou square u by dou y square is equal to 1 by c square dou square u by dou t square. Second order in time. That wave equation, you can solve in multiple ways. It depends upon the boundary condition what you impose. That is the actual requirement. And the third one is interpretation. Once you solve, you'll get some result. That result you have to interpret. When this parameter increases, then your output will be much impressive kind of thing you have to interpret. Otherwise, no use. Depending on your demand, you have to interpret. That is another part. Then validation. What is the guarantee that your model is valid? So you have to take some data, actual data, experimental data, you put in your model, then both the results should be the same. Or otherwise, someone done a case, you are extending the case, so you assume that your extension is not happen, then both persons should give the same results. Kind of validation you have to do. Then if you are not satisfied, you have to repeat the process. That's it. You have to repeat the process. Again, same thing will come, somewhere you can improve. When you are satisfied, then you can stop, you will get some output. Once the model is developed, you will get a lot of information. I don't know whether you heard about NSUP and NCAR, National Center for Environmental Prediction. What they do, they have created data for environmental data. For example, temperature at Tirupattur. For today, every minute or every hour, they know the temperature. Today we have 45 degree. They know some 20 years before. They have the data, how they created, not with experiment, not with observation. They have huge models, gigantic models. You know, huge computers they have. And the transport equation they make, they assimilate this thing. There will not be much difference. I have used the data, not will be much difference. 45 become 42 or 43. That's all. Error will be there, but because it is predicted. There is another thing like Paleolithic climatic model. Paleolithic, you know, Paleolithic era. That time, what was the temperature at a point? They are able to predict because of model. When I completed my MSc, I applied for foreign PhD fellowship. So that time, I think, Sweden, Sweden, this one university, they have this project, Paleolithic climatic model. So I attended the interview over phone because that time you don't have other facilities and all. So after interview, they told you are not fit for this job, this PhD fellowship. The reason is I don't have a strong statistical background because they use all the hypothesis assumptions and all the estimation because it is just estimation, statistical model, not mathematical model. So they told your qualification is quite different, so you are not eligible. Then you know, usually when you know that you are in the first two, I am the second, I know. Someone else is much more qualified. I started requesting, sir, please consider, I will learn all the strategies, I taught strategies I can do because we are not mature enough that time. But they don't listen. They told, no, this need much more experience and a lot of fund we are spending. I didn't get the fellowship, that's it. That's order. So Paleolithic climate also you can predict. But when you predict, you don't need the much accuracy. You want to know what is the temperature, whether it is 100 or it is 40 at a point. But they can predict with a plus or minus 5% error. So that kind of models we have still. And across the globe, every 110 kilometers, 1 degree. You know that globe is round. 1 degree means nearly 110 kilometers or 100 kilometers. Every 100 kilometers, these models can predict. If you want to improve your computational facilities, should be much more. Okay. So challenges in modeling using differential equation. I am talking only about differential equation now. You might have heard about differential equation, correct? What is the differential equation? It is an equation that contains differential coefficient, correct? I have only less time. I'll just move fast. Which contains differential equation. You know about differential equation. You know how to solve it. It is not that easy to solve. What you have studied is linear and nonlinear differential equation. You studied only linear differential equation, correct? First order equation, higher order equation, equation with a constant coefficient. You didn't study equation with variable coefficient, but you have studied Cauchy-Euler equation, correct? Cauchy-Euler equation. X square y2 dash plus xy dash plus. That itself we struggled, correct? So, but other equation we cannot solve. So what we have done, we have used power series. It is almost a series solution. There you struggled a lot because you had to analyze all these things. regular singular point, irregular singular point. What is the other things? There are a lot of models, methods you can do, but still it is very difficult. But you can solve that kind of problem with a variable coefficient also. Okay, then just let us leave those things. Then what about the nonlinear differential equation? You never studied in curriculum. How to solve a nonlinear differential equation? What do you mean by nonlinearity? What do you mean by nonlinearity? Nonlinearity is multiplication of dependent variables. U is the dependent variable, U into U square. Or U into dou U by dou Y or du by dou Y. This is nonlinear. Nonlinear means the variable itself is interacting itself. So you cannot extract U alone from the equation. You cannot solve it easily. So how you solve nonlinear equation? This is a hot topic. This is a hot topic. Even now we are not able to solve analytically. I mean analytically. So we put numerical solution. There are many numerical solutions, approximate solutions and all. If you can solve analytically, definitely that paper will get a lot of citation. Today I'm talking about an analytical technique which can solve my problem, what I'm going to model. Just come to the next one. Once again. So that's why I just marked the nonlinear equation over there. Then, but you should know what is the type of boundary condition you have. There are several types of boundary condition. First one is Dirichlet's. Dirichlet's, it is on the boundary with constant conditions. Then Newman, it is derivative condition. Then another one, this one, Robin type of condition, it's a mixed boundary condition. Derivative condition as well as constant conditions like that. It's very difficult to implement this one in a differential equation. So that itself is a specialization. I can say I was specialist in Robin type of boundary conditions. I can say. The problem is much more complicated. So solving a differential equation itself is difficult. Solving for different boundary conditions itself is difficult. You have to again specialize on that with the different methods and all. Next. This is a method which is helpful for solving differential equation. It's called a differential transform. Differential transform. What do you mean by a transform? When you are not able to do something, you will just transform to some other way, then you will understand. See, for example, I'm giving something to you. I'm giving a textbook in an ulta, upside down. You cannot read it. Can you read it? What is the problem? You can read it if you look like this. But it's very difficult for you. So what you do? You will transform it. Then you are able to read it. Then you will just bring back to the actual position if you want. That is a transformation. In real life, you have a lot of transformation you have. So you are comfortable with something, then you will make it that way and then you will solve it. Here also, differential transform is there. We use the differentiation for the concept. You have integral transform. For integral transform, what do you do? A lot of Laplace transform and integral transform. You know about this one. You integrate, you will get something else. Domain will get changed. Time domain to frequency domain. And then you solve the algebra, it become an algebraic equation. You solve it, you will get the inverse transform and do that. Same thing we do differentiation and we'll get transform. That differentiation is nothing but Taylor series. You know what is Taylor series? So nth term is now fn of a by n factorial. That coefficient is the transform of that particular function. If you have a function, you write a Taylor series, then differentiate it, nth term, what is the coefficient? That is the transform. So this transform is called differential transform. This can be applied to solve nonlinear differential equation. Next. So here, this is something like how to apply transformation for different result. For example, y into z, product term, how will you apply differential transform all? My time is very limited, so I will not stick on this one. I just tell that how to do it. Next one. Yeah, this is a differential equation. You all know very well. Is it a simple differential equation? What is there? It is simply u dash plus u square t is equal to 1. Very simple, correct? Very simple. No. It's very difficult because u square is there. You cannot do that. Nonlinear differential equation. You cannot solve with any method what you have studied in class. You ask your teacher to solve it. He will escape. Because they have not studied a nonlinear equation, how to solve it. Nonlinear in the u square term is nonlinear. So to solve this one, we applied, of course, dimensional analysis we have done. Dimension we have deleted. Scaling concept. That is another concept. That's why the right-hand side I have written. T star is defined as u infinity by g into t. U star is moved to u. U infinity become as a constant. We define that way. Those quantities are without dimensions, without scales. Okay. So our new equation is u dash t plus u square t is equal to 1, u 0 is equal to 0. See, it is very difficult to understand all these things in 5 minutes, but try to get the concept, points. So then you can go and explore how to apply DTM and all these things you can understand. Here I applied in a differential transform. First one is a derivative term. So when you derivative, as per the rule I applied, I got a linear equation, algebraic equation. Then u square term, as per the rule, it becomes sigma u r u k minus r. Then 1. Transform of 1 is delta k. This is purely based upon rule. If you go through the rule, you can do this one. Then I have an algebraic equation, recurrence relation is. From the recurrence relation, I can find all the coefficients. Go to the next one. Next. See, I got the solution here. I got all the terms, u1, u2, u3, etc. Then next, I got the solution, ut. U is the required solution. I got it as a series, t minus tq by 3 plus 2t raised to 5 by 15, etc. So I got a solution. But actual solution, this differential equation, there is a closed form solution, that is tan h in red color. But actual solution is just like you can see, it is not matching. At some point it is not matching. Why? Because of convergence. Because I have a series, you see the series. That series is not convergent actually after some domain. So convergence is a great issue. How to solve this one? We have applied a lot of methods like here, stepwise procedure and Pede approximation. We will reduce the interval size to small. Every interval will calculate. We will proceed to next one like that. We calculated. So that is forced convergence we created. Or Pede approximation also. No, previous one. Pede approximation we had, and now you see both the curves are coinciding. So we made convergence. So we got a solution now. So this technique is very successful, but only the problem is with convergence. So you should also derive expertise to get convergence actually. And the next one. I'm talking about a problem, fluid flow problem. The first one, you just said that, usually when it rains, the water will deposit in the soil. So that is what it is shown over there. Because of potential energy, water potential energy, it will filter through the soil and it will to the groundwater reservoir. Or if it is like a horizontal flow, there it is vertical flow, but horizontal flow, in the right hand side potential is high because water level is high. And you have a soil bed and it will penetrate through the soil bed and then there will be a balance. But how it penetrates the soil bed is a question. Can we model it? Yes. I'll show some model based upon this one, the movie one. Maybe you're bored with mathematics, now we'll see a movie. Yes. If your terrain is a sandy thing, it will move like this. If it is silt, it will go like this one. It's a clay. You see, it is different, flow is different. Is it? If it is granular, this is the way it moves. If it is patchy, it's not fast actually. It will go like this. If it is prismatic, subangular blocky. So for different soil, this filter will be different. By filtering velocity and all these things will be different. So this is another, somewhere you have rock. So then you have to take a diversion, that kind of thing. So a lot of different cases are there. And capillary is also there. Capillary means it will go up also. Because you know what is capillary. It will not simply, the other places, gravity will work. But capillary means, because of capillary rays, it will move in a zigzag way. That's it. The next movie. Yes, there are 3 different experiments. There are different sand samples. One is sandy loam, another one is loam, and another one is clay. And I have fitted with a pipe. So the water is dipping, but see the filter velocity. You can see this one. This is an experiment. You can see this. The first one velocity is more. The jet formation is more. Second one, it is bit less. Third one is too less because it is clay. Clay don't have, porous kind of thing. That's all. But if you want to change the parameters and do it again, it's very tough to do the repeat the experiment. But if you are doing mathematical model, it is quite easy for you. So I'll tell you how to do this mathematical modeling. Just come to the next, the slide. these are the things movie I have shown. Yeah, actually this sand is a porous medium. Porous medium. So what is a porous medium? You have you have mass and you have void spaces inside. So how to model porous medium? Total volume divided by pore volume. Pore means a gap. The ratio is called phi. You can see phi is defined. Phi is equal to maybe in the next page. So they have different porous materials. So there you can see that there are a lot of, these are different porous materials. Open cell ceramic, foam, laterite. Laterite, no, that we are using for house construction and all. This is a really a flow problem because winter time, it will absorb water and heat, all these things. So the electricity consumption, all these things, you have to do scientific study. We are not doing it, but you know, for Western countries and all, power is very costly. So they do all the power analysis and all kind of thing like that. So what they do the testing for each laterite kind of thing. So then human skin is a porous thing. That is why sweating, you know, is happening. And there is a new treatment kind. You just paste your medicine here in a strip. It will, over a period of time, it will absorb, and that is a kind of treatment. So these are all purely based upon the studies. Next. This is a kind of porous medium. The first one, no spaces in between. Another one, unconnected spaces. Spaces are there, but not connected. Another one is connected pore spaces. Only with connected pore spaces we are discussing now. Otherwise, there is no flow. The next. Yeah, next. Yeah. See, when you think about flow problems, we use Navier-Stokes equation. Those who are interested in Navier-Stokes equation can understand. But here you cannot apply Navier-Stokes equation because you have porous medium inside. So you have to, that porous medium means flow will not be fast. So that effect you have. So the law concerned to that one is called Darcy's law. Darcy's law is very clear. Q means filter velocity. How it is filtering? Proportional to delta P. Delta P is the pressure gradient. If pressure gradient is more filtration. That's it. So initially we have Darcy law. But later they understood it is not just because of the porous media. The boundary also will affect. So the model got improved then. So next model. This problem, you please see that. Yeah, we consider a porous medium. We have chemically inert porous medium I have shown there. Means the channel is filled with the porous medium, which is chemically inert. The next. Yeah, this is the model. Please understand the first term. That is pertaining to the boundary. Because boundary, there will be a friction between the boundary and the fluid. And viscosity is also available. But because of the friction with the boundary, effective viscosity will be less. So there are two kinds of viscosity. One is actual viscosity, another one is effective viscosity. Okay? So we'll just generate a parameter called mu by mu dash. That is a parameter called lambda. Okay? So the first term corresponding to the boundary effect, second term corresponding to the porous medium effect, third term, that is U square, that is inertial effect. Because something is flowing, the porous medium is stopping that one, so inertial effect will be there. Actual, what you are expecting, that will not be there. So your velocity is much less than what you are expecting. So we included one more term in the model, that is rho CB root K by U square. And right hand side, what is called pressure gradient, because something should pull. I have shown what is pressure gradient. Because you have high potential, you have low potential here. So that pressure will pull this water through the soil. So right hand side, that is the thing. Left hand side, all the terms. First one is boundary effect. Second one is porous medium effect. Third one is inertial effect of the porous medium. This model is called Darcy-Brinkman-Forstner equation. So I have solved this equation using differential transform. Differential transform. It's not simple actually, but in the next slide you can see the solutions. So these are the process of solution. I'm not going in detail. If you want, I can share the slides. So we got all these parameters, dA, lambda, and Re. The next is solving also is very challenging because actually this is a boundary value problem. Upper boundary and lower boundary. I hope you know what is a boundary value problem. This is a boundary value problem. We convert it as an initial value problem. Initial value problem means The value is at a given single point. You can see the conditions here. U0 is equal to alpha, V0 is equal to alpha. Is it? So the conditions are at a single point. So it is a technique actually to convert boundary value problem to initial value problem. And finally, we got the solution. So what is given in the last expression, that is the solution. I use only differential transform. It is somewhat simple to apply for this kind of problem. So we got the solution. This is the solution for the first kind of problem, what I explained, that is a channel flow. Then see the graphs. Yeah, this is the filter velocity distribution for various values of dA, lambda, Re. dA means porous medium effect. Lambda means boundary effect. And Re means, though it is Re, we say F. F means Fauchemer effect, drag effect. This problem is drag problem. So you see, when dA is 5, we have the first curve. dA is 5 means your porous is not thick. When dA is 10, you got the second curve. When dA is 25, your porous medium is so thick, definitely velocity is not fast. That's what you have observed there. So from the model, we got the result. We created the model, we solved it, we got the same result. What you are seeing in the movie. Okay, next one. Yeah, this is the boundary effect. I'm wearing the lambda. So lambda is 0.8, 1, 1.6. So what is happening? At that boundary effect, you can visible. Only in boundary, different filter velocity. Boundary is very, very visible. This much change is visible from the model. So, but central now, this is not visible. This is because boundary will, due to the boundary layer friction, there is slight difference in the viscosity. So that viscosity more means filter velocity is less, correct? More viscous, more sticky, will not move fast. So I got that effect in the boundary actually. It's a really a good result. So another boundary also the same result we got in. And third one is about Fauchemer effect, drag effect, or inertial effect. You have something porous medium, something is moving, but this will oppose the force, oppose the, or we say it is as inertia. What is inertia? Everybody continues its state of rest or of uniform motion. So if it is moving, it has a tendency to move. If it is staying, it is having tendency to stay. The porous medium is staying there. So it is having inertia. When it interacts with the fluid, it will share its inertia to the fluid. Because of that, fluid velocity will be less. This is too, the graph you cannot easily see because our lines are so thick. So I have plotted the values here. Yeah, if you check the values, I'm not going to read all the values. When you check the values, you can see the difference. Okay, just skip all these things. Yeah, I'm not going into detail of this one. This is a two-dimensional problem now. Two-dimensional problem. Previously only channel. Now this is a rectangular box. That means you have X variation and Y variation. So what is happening like, this is the equation. Previously only mu dash into dou square U by dou Y square. That's all. Now you have mu dash into dou square U by dou Y square plus dou square U by dou Z square. Minus mu by K U. Minus rho CB root K by U square dP by dx. So dimension is increased. So equation I have added one more term. That's it. Then condition also, accordingly you have to define the condition. Then next step is solution. Of course, this particular problem is somewhat difficult to implement. We know how to do it, but implementation part, we will face a lot of challenge. You will not get convergence, you will not reach the solution, etc. But if you really practice this one, it will be helpful for you. So ultimately, I want to say that because my time is very restricted. So you start with a simple equation. If you want to model something, you understand the problem first. What are the parameters over there? And what you want to predict or want to describe. Here I want to describe the filter velocity. Then there are many techniques. That technique also we want to learn. Then developing the model is based upon some rule. This is called Darcy-Fauchemer-Brinkman equation. It is fundamentally based on F is equal to ma. All equations mostly. Most of the equation related to motion, it is by Newton's second law of motion in a disguised form. Most of the equations are like that. So this particular equation is developed by Darcy, Fauchemer, and Brinkman. Over a period of time, they developed those things. So to study any porous medium, you are using this one. As a modeler, you are also not going to define any new rule. That's what I want to say. So whatever is existing rule, based upon that, you have to create the equation. Then you have to impose the boundary condition. Then you identify a suitable method to solve it. Once you solve, you should ensure that your result is correct. That is your responsibility. When the result is correct, you can declare that my model is perfect. Then you can sell it. That's what I want to say. You are solving for some people, they have a problem, you want to understand. So definitely mathematical equations you are telling that you are a mathematician. So if you are basically, if you have some skills in differential equation, you have to learn how to be a modeler. By experience it will come, by experience. So you can try with simple models. You don't need to go for this kind of differential equation at all. Small differential equation. Try to predict. Because someone will be there to enjoying those applications. The layman don't know all these things. You use a simple differential equation and predict something. Definitely there are domains, but people don't know that they can get a solution using this one. In this room, if you want to study Newton's law of cooling, you can apply, correct? For room temperature and all, Newton's law of cooling, first order differential equation. Spring mass system. Your car, you have 4 springs. Your shoes, I'm designing this shoe. There are spring inside. They're not putting a spring, they use foam. Do you think that simply they put some foam? No, they're studying it. If I apply this much of weight, they also calculate to what extent the weight can go. That's why the shoes are very costly. Because some shoes, branded shoes are very costly actually. Because they do all this kind of analysis, you put a foam, they create a foam of that kind. How it will absorb the shock, etc. So they use second order differential equation to model that. Then all this, the elasticity and what do you call it as? For a spring, what is a spring constant is there. For here also when you apply force, it acts like a spring. Human body is a spring actually. It's a spring mass system. Because this neck holds this much of weight. Definitely, it absorbs the shock. All these muscles will absorb the shock. So you can see this kind of studies in this one. So biological studies they have done. So it is up to you how you are applying mathematics. Take something, understand the problem, use your own equations, try to solve it. If it is not matching, throw it, improve it. Again, do the same thing. Over a period of time, you can be a good modeler, and you can say that I am basically learn a lot of mathematics. There is no hard and fast rule that you are solving using differential equation. You can use anything, any mathematics. Okay? So with this, I am just concluding. Thank you so much for listening. And the last one, the references. These are the references. So the previous one. If someone is interested with this work, I can send the right reference for this one because you have to start from some platform. You cannot create magic at all. You have to read some paper, you have to understand slowly over a period of time. So we got some concept on this one on modeling. I'm grateful. Thank you so much. We'll meet again.
Thank you, dear sir, for enlightening us with your valuable knowledge and sharing day-to-day life examples. I'm sure each and every one of us present here would be ignited by their minds and have a longing crave in the upcoming research era by your provoking address. Thank you, dear sir. A very good afternoon to one and all present here. Let's start the session 1 on fixed point theorems and on generalized metric spaces. It's my honor and esteemed privilege to welcome the resource person of this session, Dr. Maria Joseph, Assistant Professor, St. Joseph College, Trichy, to this forum. Mathematics is more like rope climbing a mountain to get at the top than stopping at scenic overlooks to get a glimpse in various directions. Good advising can help you reach the summit more quickly and purposefully. And we have one of the good advisors to help us to reach the summit, Dr. J. Maria Joseph, and I'm proud to say that he's our alumni who did his undergraduate in the year 2000 in this campus. He has completed his B.Ed at St. Xavier's College of Education, Palamkote in the year 2001, and he did his PG and MPhil in St. Joseph's College, Trichy. He completed his doctoral degree in the year 2013 at Bharatidasan University, Trichy, and he has 21 years of teaching experiences and 16 years of research experiences. He has attended many conferences and workshops, and he has also delivered many significant lectures in various colleges. He has published a book on fixed point theorem and best proximity points published by the Lambert Academic Publishing, Germany. He has also cleared SET exam and CSIR net, and he has also received College Management Special Award for the years 2009, 2011, 2014, 2017, awarded by St. Joseph's College, Trichy. He has presented more than 20 papers in various national and international conferences, and it's indeed my pleasure in welcoming such an eminent person in our midst. Welcome, dear sir. May I now invite Dr. J. Maria Joseph, the Assistant Professor, St. Joseph College, Trichy, to take over the session. I look forward to a very stimulating and informative session, sir. Welcome you, dear sir.
The most respected Dr. AGM, my teacher, Dr. Ajay, convener, Professor Savida, other learned colleagues, student friends, a pleasant good afternoon to you all. I won't take much of your time. I hope you are all hungry as well as angry. I could understand. I take just 30 minutes. 30 minutes. I will highlight only fixed point theorems. It's a pure mathematics. It comes under pure mathematics. Most of the students find it difficult to do research in pure mathematics. Initially, I also found it difficult, but once you get into that, you will enjoy like anything. So after this session, at least a student, a scholar will impress or attract from this session. I'm not going to take everything in detail. Besides, I motivate you, I give you a few steps to understand what is fixed point. What is fixed point? How you have to carry over a research from that area. Initially, this is not my area. When I was doing research, I did another topic. After my PhD, I switched over to this area. Such an interesting topic. You can enjoy. Within 30 minutes, I will complete this session, I promise you. If it exists more than that, give you a big round of applause, I will finish it. Hope it's a gentleman agreement. We'll do it. Shall we go to the presentation? Fine. Actually, Stephen Bannock, in the year 1922, Stephen Bannock, he laid foundation for this fixed point theorem. What do you mean by fixed point? A map, self map. You know, self map, domain, codomain, same. After the transformation, it remains the same. Whatever input you give, you receive the same output. So it is invariant under transformation. It's called a fixed point. So you are all aware of what is Lipschitz constant. So it's a mapping from x to x. The constant, that constant is less than 1 means it's a Lipschitz constant. For example, closed interval 0, 1 to closed interval 0, 1, you can define Tx equal to x over 10. X over 10. What happens when you take modulus? X by 10 minus y by 10 modulus of. So 1 over 10 comes out of the modulus. K equal to 1 over 10. That is Lipschitz constant. So geometrically, how do you find out fixed point? What is the fixed point? How do you find out this is the map, domain, codomain, self map? The function is defined as f of x equal to or g of x equal to x square. What are the fixed point for this function? Suppose I give f of 0, what happens? F of 0 square equal to 0. Similarly, f of 1 equal to 1 square. These two are fixed point for this map. How do you find out? Draw a line. So this is a curve. I draw a line. You can see here and intersecting points. Intersecting points. These 2 points are fixed points of the given map. So this is geometrically I have given. Even we can do by solving these two equations, y equal to x. So what happens? Y equal to x. The left hand side we have x, right hand side we have x square. So x square minus x equal to 0. Then take x common, x into x minus 0. So x equal to 0 and x equal to 1. So this is the idea to find out fixed point for any map. Take. So only these 2 points. So this is the another map. So maybe by quadratic equation, we need to find out fixed point, draw a line. Draw a line means y equal to x. So this is not a fixed point. You can see this, the intersecting points. So 1, 2, 3, and 4. These are the fixed point. So what happens if you give t of 1 equal to 1 in this equation or in this map, you will receive the answer is 1. When you give t of 2 equal to 2, 2. So something like that. This is the iteration. This is the iteration is given. So this is also called the Picard's iteration. So if you are interested in ordinary differential equation, you can relate this idea in fixed point. Now, okay. This is the another mathematician. His name is Schauder. He has come up with this idea. After the Banach contraction principle, he has given that every continuous map which is close to bounded convex subset of R power n has at least one fixed point. He has given the assurance that fixed point exists. If it satisfies all these conditions, 4 conditions, nearly 4 conditions. If you drop any one of the conditions, we will not get a fixed point. Another beautiful theorem. If I get a board or time, I would explain this. Unfortunately, I didn't get it. But this is another important theorem. Suppose if you want to do research, this theorem will lay foundation for your research. If you take any map, if you construct any map which should be continuous, closed, bounded, convex. For example, f from R to R, f of x equal to x plus 1. This map will satisfy all these conditions. Unfortunately, this is unbounded. So there will not be possible for fixed point. Similarly, f from open interval 0, 1 to open interval 0, 1, f of x equal to x square. This is not closed, so that we will not get any fixed point. Something like that. If you drop any one of the conditions, we will not get a fixed point. So weaker section. This is my topic actually. This is my topic. Generalization of fixed point. Generalization of fixed point. Usually we know metric space has to be satisfied with 3 axioms. What are the axioms? Non-negativity. Self-distance of a point is 0, which means d of x comma x equal to 0. And then symmetry, triangular inequality. Here, the B metric space is the weaker section of the metric space. And here we have S is greater than or equal to 1. S is greater than or equal to 1. If S equal to 1, it is a metric space. It's a metric space. Here I have given one example. So I take this is the map. So d of x comma y, d of self distance is 0, where we get S equal to 1.5. S equal to 1.5. This is not a metric space. This is not a metric space, but a B metric space. So which means generalized metric space. One of my PhD scholars has done is research in generalized metric spaces, S metric spaces, partial metric spaces. All these are generalization of metric spaces. Here, self-distance of a point is 0. Self-distance or a point, the distance from a point to point itself is 0. Whereas partial metric space, self-distance of a point need not be 0. So these are all some beautiful results, beautiful concepts. The young researchers, you can go through this. In LP spaces, defined map defined like that. So here, what would be the S? What would be the S? Here S equal to 2 to the power of P. What about P? P is greater than 1, which means S is greater than 1. It is B metric space, but not a metric space. Sometimes metric space can be a B metric space. In general, it is not true. Multi-valued map. What does it mean, multi-valued map? Multi-valued map. Here, the codomain would be 2 power y. Codomain would be 2 power y, where self-map x to x. When you define fixed point in multi-valued map, it has to be satisfied x naught in t x naught. So a point x naught is said to be fixed point of the multi-valued mapping if x naught in t x naught. So I have given one example. So host of space. For your information, in 2016, we have presented fixed points in S metric space. Earlier, all have given their research only in single valued map. First time, we have come across fixed point theorems on multi-valued mappings in B metric space. It was globally accepted and appreciated. So, for me, I have many citations only in this. Since earlier nobody has done any, they did not find any fixed point on multi-valued mapping in S metric space. There were many fixed points in S metric spaces. They have not tried on multi-valued mappings. You can try. So this is the results, and Springer it published in 2016. It could be like a Banner contraction principle. So x comma d be a complete metric space with S greater than 1, then this the map, generalized contraction mapping, then T as a unique fixed point. This is our theorem. So if it satisfies this condition, a unique fixed point, not many, then